Black holes may sound like science fiction, but there is significant evidence to prove they are real. Of all the far-out concepts in astronomy, black holes may be the weirdest. A region of space where matter is so tightly packed that nothing, not even light itself, can escape. These dark behemoths present a pretty terrifying prospect, too. With all the normal rules of physics breaking down inside them, it's tempting to dismiss black holes as the stuff of science fiction. Yet there's plenty of evidence, both direct and indirect, that they really do exist in the universe. As a theoretical possibility, black holes were predicted in 1916 by Karl Schwarzschild, who found them to be an inevitable consequence of Einstein's theory of general relativity. In other words, if Einstein's theory is, and all the evidence suggests it is, then black holes must exist. They were subsequently put on even firmer ground by Roger Penrose and Stephen Hawking, who showed that any object collapsing down to a black hole will form a singularity where the traditional laws of physics break down, according to the University of Cambridge. This has become so widely accepted that Penrose was awarded a share in the 2020 Nobel Prize in Physics for the discovery that black hole formation is a robust prediction of the general theory of relativity. In the 1930s, Indian astrophysicists looked at what happens to a star when it has used up all its nuclear fuel, according to NASA. The end result, he found, depends on the star's mass. If that star is really big, say 20 solar masses, then its dense core may itself be 3 or more times the mass of the Sun, collapses all the way down to a black hole, according to NASA. The final core collapse happens incredibly quickly, in a matter of seconds, and it releases a tremendous amount of energy in the form of a gamma-ray burst. This burst can radiate as much energy into space as an ordinary star emits in its entire lifetime. And telescopes on detected many of these bursts, some of which come from galaxies billions of light years away, so we can actually see black holes being born. Black holes don't always exist in isolation. Sometimes they occur in pairs, orbiting around each other. When they do, the gravitational interaction between them creates ripples in space-time, which propagate outward as gravitational waves. Another prediction of Einstein's theory of relativity. The first discovery, involving the merger of two black holes, was announced back in 2016, and many more have been made since then. As detector sensitivity improves, other wave-generating events besides black hole mergers are being discovered, such as a crash between a black hole and a neutron star, which took place way beyond our own galaxy. At a distance of 650 million to 1.5 billion light-years from Earth. The short-lived, high-energy events that produce gamma-ray bursts and gravitational waves may be visible halfway across the observable universe, but for most of their lives black holes, by their very nature, will be almost undetectable. The fact that they don't emit any light or other radiation means they could be lurking in our neighborhood without astronomers being aware of it. There's one surefire way to detect the dark beasts, though, and that's through their gravitational effects on other stars. In addition to black holes created through stellar collapse, evidence suggests that supermassive black holes, each millions or even billions of solar masses, have been lurking in the centers of galaxies since early in the universe. Another piece of evidence for the existence of black holes is spaghettification. What, you might wonder, is spaghettification? It's what happens when you fall into a black hole, and it's pretty self-explanatory. You get stretched out into thin strands by the black hole's extreme gravitational pull. Luckily, that's not likely to happen to you or anyone you know, but it may well be the fate of a star that wanders too close to a supermassive black hole. In October 2020, astronomers witnessed this shredding, or at least, they saw the flash of light from a hapless star as it was ripped apart. Fortunately, the spaghettifying didn't happen anywhere near Earth, but instead in a galaxy 215 million light-years away. So far we've had plenty of compelling indirect black holes, bursts of radiation or gravitational waves, or dynamical effects on other bodies, that couldn't have been produced by any other object known to science. But the final clincher came in April 2019, in the form of a direct image of the supermassive black hole at the center of active galaxy Messier 87. This stunning photo was taken by the Event Horizon Telescope, a slightly misleading name, because it consists of a large network of telescopes scattered all over the world rather than a single instrument. According to NASA, the more telescopes that can participate, and the more widely spaced they are, the better the final image quality. The result clearly shows the dark shadow of the 6.5 billion solar mass black hole against the orange glow of its surrounding accretion disk.